All right, so I'm going to explain the answers to the test review, and I'm going to start with number 1. So up here, I just want you to see that the instructions do specifically say to use long division. I did take a shortcut because A and B are both in that linear binomial format of x plus or minus a number, so I was able to use synthetic division. So I did that for A and B, and since my remainder for A was negative 36, I know that negative 1 is not a 0, and the factor x plus 1 is not a factor of the polynomial. For example B, I used synthetic division again. I got a remainder of 0, which means that 2 is a 0 and that x minus 2 is a factor of the original given polynomial. And on C, we cannot use synthetic division because the divisor is quadratic. So we have to go ahead and use the long division. So what you do is you ask yourself, how many times does x squared go into x to the 4th, or what do I need to multiply x squared by so that it becomes x to the 4th? And of course, that's x squared. So then you take x squared and multiply by this entire expression, and that's what I got here. And then you subtract. Then how many times, or what do you need to multiply x squared by to turn it into negative 6x cubed? That's negative 6x. Multiply negative 6x by the entire divisor, and get that. Subtract. And then ask yourself, x squared times what gives you negative 4x squared? And that's negative 4. Multiply negative 4 by the entire divisor, and subtract. We have a remainder of 54x. If x squared plus 5 was indeed a factor of the dividend, the remainder would be 0. Since the remainder is not 0, x squared plus 5 is not a factor of the original given polynomial. Number 2 and 3 ask us to divide and to write the answer in a particular format. So we're going to have the divisor times the quotient plus the remainder. So that is what I went ahead and did right here. So x squared times what gives you x cubed? Well, that's x. Multiply x by this entire expression, and then subtract. X squared times what gives us negative 2x squared? Well, that's negative 2. Multiply negative 2 by this entire expression, and subtract. We get a remainder of 2x minus 4. So we write our answer in the format where we take the divisor, right here, multiply by the quotient, right here, and add the remainder, right here. So number 3 is just like that. Long division, writing the answer in the format of divisor times quotient plus remainder. Four and 5 ask us to use synthetic division to find the quotient and the remainder. So we need to remember that for synthetic division, we need to have all of the powers accounted for, and we do. We've got cubic, squared, linear, constant. With a third degree polynomial, we want to have 1, 2, 3, 4 terms. And we have the opposite of this number goes on the outside. Bring down the first number, multiply, add. Multiply, add. Multiply, and add. And we get a remainder of 155. So 6, 16, 52 represents the polynomial 6x squared plus 16x plus 52. We know it's going to be a quadratic quotient because we started with a cubic dividend and we divided by a linear divisor. Number 5, similar problem. Cubic, quadratic, linear, constant, all numbers accounted for. Just put those coefficients right in there. Put the opposite of this number out here. The reason that we do the opposite is because we are trying to find out if x minus 5 is a factor. So if x minus 5 equals 0, then x equals 5. So that's the number that we put on the outside of the synthetic division. So we bring down the 1, multiply, add, multiply, add, multiply, and add, and we get a remainder of 120. 722 represents the polynomial x squared plus 7x plus 22. Once again, we know that this is a quadratic quotient because our dividend was cubic and our divisor was linear. X cubed divided by a single x leaves us with an x squared. Number 6, we are asked to evaluate a polynomial function using synthetic division. So with this one, we do not change the sign of here. We just take that exact number and put it over here. And similar to that last problem, the reason we don't change the sign in this case is because this is x. X is -2. So if I wanted to rewrite that so that it was set equal to 0, I would need to add 2 to both sides of the equation, which would leave me x plus 2 equals 0. And so once again, when it's in that factor format, we do the opposite. If we are evaluating, we just take that exact sign because x is already isolated. So we have a remainder of 36. So that means that for this function f of x, when we plug a -2 in place of every x here, we should get 36 as the output. Number 7, we have a 4th degree polynomial, and we do not have a cubic, quadratic, or linear term, so we need to make sure we put zeros in as placeholders in the synthetic division. We are testing to see what f of -2 is, so we'll put that -2 on the outside, bring down the 1, multiply and add, multiply and add, multiply and add, multiply and add. We get a remainder of 0. So right here I have a little PS. That does mean that x plus 2 is a factor of the polynomial x to the 4th minus 16. Number 8 and 9 tell us to use synthetic division and determine whether the given numbers are zeros of the polynomial function. So once again, in order for a number to be a 0 or a solution to the polynomial, we need to get a 0 as a remainder. So when we use synthetic division with -1, our remainder is not 0, so -1 is not a 0 of the function. It's not a solution. For +5, we do get a remainder of 0, so that does mean that 5 is a 0 of the function or a solution to that polynomial. Number 9, we're asked to test -1 and -2 with this 4th degree polynomial here. We've got all the powers accounted for, 4, 3, 2, 1 constant, so we don't need any placeholder zeros. So we can just use a synthetic division. We see that we have a remainder of -20 when x equals 1. When x equals -1. So -1 is not a solution or a 0. And we get a remainder of 0 when x equals -2. So -2 is a solution. And on to page 2. For 10, 11, and 12, we were asked to factor the polynomial and then solve the equation f of x equals 0. So we want to factor and then take those factors that we get and then find the solutions that we would have based on those factors. So this is a little bit tricky just because the instructions specifically tell us to factor, and we are used to factoring using grouping, and we cannot do that with this. And we actually can do factoring by grouping for number 10, but I went ahead and did the synthetic division here. You are going to use the rational root theorem to test different solutions to see which ones give you zeros as remainders. So for number 10, I tested +1, I got a 0. And when that happens, when you get a 0 as a remainder on your first try, first of all, celebrate that because that's awesome. But then what you can do, instead of starting back at the original dividend, you can take your new quotient as your new dividend and then start with the next possible rational solution from there. So that's what I did. I got a 0. And then from there, I tested -1 and I got another 0. So 1, 0, -2 represents the polynomial x squared minus 2. And if we solve that algebraically, we set it equal to 0 and solve by taking the square root of both sides. So we get that x equals plus or minus root 2. This is not a rational number. This is irrational. And notice, by the way, that it comes in a pair. Irrational numbers come in conjugate pairs. So we would not be able to get these two numbers using the rational root theorem because they are not rational. So 1 and -1 are our only rational solutions to number 10. For number 11, once again, I started with 1 and celebrated when I found it to be a factor. And then from there, you can continue on with your synthetic division and you can keep testing values. Notice, I started with +1. I usually would go to -1 next, and then +2, and then -2. So I would have several attempts in between here, except I noticed that after dividing out a linear term here, this quotient is quadratic. And I can solve a quadratic by factoring if it's factorable, or by the quadratic formula if it's not factorable. So my factors of 6 that add up to 5 are +3 and +2. So I was able to know from this step and factoring the quadratic that these two factors will work for this polynomial as well. But I went ahead and verified them with synthetic division, using -3 out here, getting a remainder of 0, and then using -2 in my last step and getting a remainder of 0. And then I rewrote all of those as their own factors. So the factored form of the original given polynomial is x plus 3 times x plus 2 times x minus 1, which generates the opposite for the solution, because we would set it equal to 0 and solve. So we have -3, -2, and +1. Now number 12 was a little bit of a doozy. So it did not give us a 0 when we used 1 in the synthetic division, so we had to try again. So I started with 1, I did not get 0 as a remainder, so I had to try again. I went to -1, I did not get 0 as a remainder, so I had to try again. I went to +2, and yes, I finally got 0 as a remainder. So 2 is a 0 of this polynomial, and x minus 2 right here is a factor of this polynomial. What remains is a quadratic in the form of x squared plus 7x plus 12, which is factorable. So I broke that down into factors based on the numbers that multiply together to give us 12 and add together to give us 7, which are 3 and 4. And so here is my factored form of this polynomial function, and that generates the zeros that are the opposite of these here, 2, -3, and -4. For number 13 and 14, we are given solutions or zeros, and we want to write the factored form and the standard form of a polynomial of degree 3 with the given zeros. Now, I want to point out here that none of these solutions, none of these zeros that are given to us are imaginary or radical. So we do not need to add anything to this list. Also, we're told specifically that it should be a cubic. So we have 1, 2, 3 solutions. That's all we need. So you take this and you write it with x as the opposite. And that comes from this here. So if I have that x equals -4, I want to get the factor by setting it equal to 0. So I'm going to move 4 over by addition, and I'll have x plus 4 equals 0. And there is that factor that I wrote there. So we've got x plus 4 times x plus 1 times x minus 2, and then I multiplied these two binomials together here, and then I distributed x to every single term, and then I distributed -2 to every single term, and combined like terms to get the final standard form polynomial of the product of these factors that we wrote based on these zeros. Number 14, very similar, but this time we do have some imaginary ones, but once again, it should be degree 3, and we have the conjugate pair of the imaginaries, so we do not need to add any additional zeros. So we have the opposite of 3, x plus 3, the opposite of negative 2i, x plus 2i, and the opposite of 2i, x minus 2i. I multiplied these two binomials together, and that gave me x squared plus 4, and I'm going to show you that over here using an area model. Leave it showing here for you. So if I have x plus 2i times x minus 2i, x times x gives me x squared, x times 2i gives me 2ix, x times negative 2i gives me negative 2ix, and 2i times negative 2i gives me negative 4i squared. And I squared equals negative 1, so this is negative 4 times negative 1, which is positive 4. These two terms cancel out, and we're left with x squared plus 4. For our next problem, we are asked to list all the possible rational zeros of the polynomial function 4x to the 5th minus 2x cubed plus 6x minus 12. Remember, to generate this entire list, we need to take all the factors of the constant and put them over all the factors of the leading coefficient. And then to generate the list, we want to take each numerator and put it over each denominator to generate list. So we have 1 over 1, so plus or minus 1, 2 over 1, plus or minus 2, 3 over 1, plus or minus 3, 4 over 1, plus or minus 4, 6 over 1, plus or minus 6, 12 over 1, plus or minus 12. And then 1 over 2, plus or minus 1/2, 2 over 2, we already have that here represented with the 1, 3 over 2, plus or minus 3/2, 4 over 2, we already have that here, 6 over 2, we already have that here with the 3, 12 over 2, we already have that with the 6. So now we get to move on to the denominator 4, 1 over 4 for 1/4, 2 over 4 simplifies to 1/2, we already have it, 3 over 4 completes the list because the remaining numerators will simplify to an existing number in the list. So that is all you need to do for number 15. And that's how those questions are going to be asked on the test. You're just going to be choosing the right list of possible rational solutions. Number 16, we want to find the rational zeros and then the other zeros. I used synthetic division for this. I started testing 1 and negative 1 as I usually do, and I got lucky that those worked. So starting with the original polynomial, I tested 1, got a 0 remainder, and then I used the new quotient as my new dividend, and I tested negative 1, and I got a quotient here that is quadratic. That's why we have the quadratic formula on our page here. Once you get to a quadratic quotient, then you can figure out what the solution to that would be. Now, I did the discriminant first, and I found that I had a negative discriminant, which means that I was going to have imaginary solutions. So I went ahead and built the rest of the quadratic formula around my discriminant of negative 4, and then I simplified and I got my imaginary solutions of 3 plus I and 3 minus I. So I'm going to write those factors out as x minus 1 times x plus 1, and I got those from the synthetic division, and then x minus 3 plus I and x minus 3 minus I, which I got from the quadratic formula. The last section is writing polynomial equations in factored form, okay, in factored form from given zeros, and we need to add in zeros so that we get to the degree we need, which is 5. So for number 18, we have the x value of 1. It's a whole number. It does not need a partner. But the radical and the imaginary numbers do need partners. So we have to write in their conjugate pairs. So we have also the x's of 1 minus 3x and 1 plus 3x. and then I just wrote those in their factor formats, just stacked together like that for the factored form of the polynomial. Number 19, once again, we have a rational number here, so we do not need a partner for that, but 3 minus I needs a partner, and so does 5 root 2. So we also have solutions of 3 plus I, which is the complex conjugate of this, and negative 5 root 2, which is the complex conjugate of that. Then I wrote them in their factor forms, so x equals 1/2 comes from the factor x minus 1/2, and then we have the complex factors and the irrational factors. And number 20, we have 2 and negative 3 and 0, none of which need a partner, but we do have an imaginary one which does need a partner, so we need its conjugate pair, and then we write them in their factored forms. So x minus 2, x plus 3, just x. It's the same thing as x minus 0. And then x plus 3i and x minus 3i.